Okay, so back to the the explanation of this section. So the motivational question is it possible to classically verify that a quantum system, such as a quantum computer, is behaving as intended? Okay. So there's a number of reasons why we would be interested in this question. So, so here's a little story. So like imagine that there's a company called Quapple. They sell you a QMac for the cool price of $1 gazillion, right? You take it out of the box and, you run it through its paces. So, the first thing that you probably want to try is, okay, can it factor large integers? So, one way to test this is, okay, you pick two primes, P and Q, you ask it, so you multiply the two primes together, you get some large integer n, and then you ask, can you factor n? And the computer will, if it returns P and Q, then you're going to say, okay, well, it seems to be doing a pretty good job. So, for those types of problems, like for problems like factoring, you can easily check if it's doing the right thing, right? So, for example, can verify a quantum computer can factor, right? That's so that's one thing you can do for verification. But what if you want to solve some other problem, like you want to simulate the evolution of a Hamiltonian, right? So let's say you have a local Hamiltonian H, right? Describes your, some physical system of interest. And what you'd like to do is say, well, I'd like to evolve this Hamiltonian. So there's this operator, e to the minus iht. This is a unitary operator. And you want to apply it to some initial state. Let's say it's like the all zero state or something, right? You want to evolve this Hamiltonian. This is something that you can do in polynomial time. And you want to say, given the result of this evolution, I want to estimate some observable m on this state. So this is what you want to calculate. And this is basically like what quantum computers were meant to do, to solve problems like this. So you program up this QMac using your favorite Hamiltonian simulation algorithm that's in the literature, and you run it and it spits out some number. Let's say it spits out 42. Okay. How do you know whether this is actually the correct answer? Right.
First, you have to check whether you asked the right question.
Right, exactly. Exactly. So let's say you even figured out whether you asked the right question. And conditioned on that, then you want to know if this is the right answer. And this is not so obvious how to do, right? Because like the whole point of buying this, quantum computer is it was supposed, this task was supposed to be intractable for classical computers, right? Like, presumably in general, it should take a classical computer exponential time to figure this out. So how would you possibly know whether the quantum computer was doing the right thing? So that's one reason why it's an interesting and important question to come up with classical verification schemes for these types of quantum computations. And it's not, just about being paranoid, right? Like today, people are trying to build quantum computers, and the quantum computers are trying their best, but they're very noisy and they're very primitive. So you'd like to have some assurance or some certificate that whatever answer that these computers are giving you, it's not due to noise. It's not just some noisy junk output, but it's actually something accurate. So that's like a practical motivation. There's another motivation, which is like, to me, maybe actually more interesting, which is a little more philosophical, which is that, quantum computers are not just bigger and faster versions of classical computers. They're actually qualitatively different than classical computers. One way that they're qualitatively different is that our best attempts at trying to come up with a classical description of what's going on inside of a quantum computer would require exponential resources, right? And it's really unlike anything that we've built or designed before. And so given that it's so different from anything that we're used to, it seems like it really justifies like additional skepticism or scrutiny on whether these fantastic machines that you're building could actually ever be made to work. And there's also a lot of skepticism out there whether quantum computers are possible at all. And some skepticism is more scientific than others. So for example, there's a famous mathematician who's maybe at the forefront of quantum computing skepticism. So there's this guy named Gil Kalai. And they're very publicly, they have proposals for why quantum computers cannot work in principle. And for example, Gil Kalai's main argument is that once you scale up your quantum computers beyond a certain size, there'll just be these correlated errors that actually prevent your system from doing anything that cannot be classically simulated. Or just to say it more simply, the errors will accumulate in such a way that whatever's happening in your quantum computer, it can be classically simulated. So you cannot achieve this quantum speed up. So it's not clear how much water his proposal holds. There's he doesn't come out with like a very precise model that can be refuted, proved, or disproved. But it's a serious attempt at trying to poke holes at whether quantum computers can work at a large scale. And so it's worth trying to meet this skepticism head on and trying to come up with very principled and sound ways to try to refute their arguments, right? There's this.
Henry.
Yeah.
Has this guy said anything about the Supremacy Experiment?
Oh, he said a lot of things about the Supremacy Experiment. He's given a bunch of talks, and unfortunately, I haven't watched them in detail. But I think he raises some good points, at least in the stuff that I've seen. He says that so in these, like for example, the Google's quantum supremacy experiment, they have some statistical verification for why they think that the Google's device actually passes this this supremacy test. But they actually, the Google folks used a bunch of heuristics and assumptions, for example, about the types of noise that you see in the system. And I think what Gil Kalai is saying is that this assessment of the noise is too simplistic. And it still leaves open the room that actually it's, that it's not working as well as, say, the Google folks think it is. Now, at least my opinion is that I think I do agree that the Google's noise model is too simplistic, but not in this damaging way that Gil Kalai believes that it is. So that's my opinion at any rate.
I think he even wrote a paper on that specific experiment called the Statistical Aspects of Quantum Supremacy Demonstration. For some reason, I cannot play it here. Maybe you can look it up.
Oh yeah, so if someone can find the link and maybe post it in the chat or in the Slack, that would be great, so people are curious. So he's come out, I mean, he's had this skepticism for many years, and his arguments have evolved. But I think it's a very useful, it's useful for the science, because you need people to, at least credible people, and I think Gil Kalai is very credible because he's a professional scientist, he's a mathematician, that's very accomplished. And you need them to push back on our claims that we can build a quantum computer, right? And then it forces your science to be more honest. Okay, so I think if we developed means or methods or protocols to verify whether a quantum computer is working correctly without assuming that you have a quantum computer to begin with, that would be a great way of answering this challenge. So that's kind of what the motivation behind this. So what are we going to talk about in the next 6 weeks of the class? Well, there's been a lot of progress, both theoretical and experimental, on methods for verifying quantum systems. And we're actually going to cover the more theoretical angle. So we're going to talk about, one thing we're going to talk about is a specific protocol that's due to Alex Grillo. So Alex Grillo has a two-prover protocol for verifying quantum computations. All right, so this is in this setup, in his protocol, basically we have a classical referee. Imagine that it's a classical skeptic, and they want to run a quantum computation, and they interact with, not one quantum computer, but say 2 quantum computers that are separated, right? And this should start look a little familiar to stuff we've seen before. And the referee will interact with these 2 quantum computers classically, just sending classical messages back and forth. And at the end, the referee should be able to verify whether the result of, say, for example, this computation really is approximately 42 with high probability. The requirements of these 2 quantum computers is that they're entangled, that they share quantum entanglement. So that's one protocol that we'll see. And building on ideas that go into this type of protocol where you're trying to verify that these 2 separated machines are doing something correctly, we can actually prove results that are actually they're interesting, not because they related to quantum computation per se, but because they have interests to, they have consequences for things like complexity theory, and also pure mathematics. So there's a second result that we'll talk about that's called MIP star equals RE. This is a complexity result. And it has applications to pure mathematics and also mathematical physics. And what goes into this result are basically ideas from verification. Okay, it's really central to this result. And so we'll talk about that in a couple of weeks. And if we have time, then we'll talk about another protocol, but it's slightly different character. So this time it's a single prover protocol. So you have a classical referee, and it interacts with only 1 quantum computer. So you don't need these 2 quantum computers anymore. And you can verify that this quantum computer is correct. So this is a protocol due to Mahadev. And what's interesting about it is that in order to reduce the number of provers or quantum computers you have to interact with in order to do this verification, you make use of cryptography. The cryptography is a way to sort of force this, quantum computer to do what you want it to do in some verifiable way.
Ask a question.
Yeah.
With regards to the two-prover protocol, like I don't understand why we want them to share entanglement. To me, it would seem more impressive if the computers, or easier to verify, and more impressive if they could do it without that entanglement. And furthermore, once they're sharing entanglement, I'm not really seeing in what sense they're two quantum computers. To me, they seem very similar to one quantum computer.
Okay, good question. So that's right. I mean, it would be if you could do it without them sharing entanglement, that would be great. I mean, also that would in terms of practical concerns, it would make it easier to implement this protocol, right? It's the entanglement is actually needed because without it, these two quantum computers couldn't coordinate their responses in a way that would convince you that they were doing the right thing.
But doesn't it also allow them to, coordinate some clever way of fooling me? And
Right.
I guess that's, once we see the actual protocol, we'll have to address that concern.
Exactly. So that definitely is something you have to worry about. But it turns out that the protocol will have these checks to ensure that they aren't. And for your second question, why is 2 different from 1? Well, they do share entanglement, but they're still not allowed to communicate in the sense that this computer right here does not see what you're asking the other computer. Because entanglement doesn't allow you to communicate. And this constraint is very useful. So basically, you can enforce that the in some sense that their behavior is honest. It'll become more clear when we explain how the protocol works. But those are really good questions.
Yeah. So maybe another kind of silly question: if they don't share quantum entanglement, then this basically boils down to MIP without a star, right?
Mm-hmm.
And they can choose to not share entanglement, right? Like it's up to them.
Right.
And so, like, how can you beat NEXP if they can choose to never allow you to beat NEXP by just not share anything?
Well, let's see. So I didn't quite get that, but well, I mean, I sort of get what you're saying. So, so there's one important thing that I want to emphasize is that in this protocol, these 2 quantum computers are assumed to be quantum polynomial time. So it's actually a little. I mean, it looks it looks very similar to this MIP equals NX thing that I described a few lectures ago. But there, the provers were allowed to be infinitely powerful. Here, we actually, because we want this to be, potentially a real-world applicable protocol. So the demands on these 2 quantum computers is they should be able to run this protocol in polynomial time.
Oh. Mm-hmm.
So
Okay.
in particular, they won't be able. We don't expect them to be able to solve, NX complete problems. So that's
okay.
Yeah. Does that answer your question?
Like that illustrates some difference between the 2 complexity classes that I can assume will lead to some implication that I'm not yet seeing.
Mm-hmm. Yeah. The point is that this entire protocol can be simulated in quantum polynomial time. So, cool. Yeah, any other questions about sort of the setup or the theme or anything like that? Okay, so this is where we're going. So let's dive into it. So the key workhorse behind these two results is going back to something we covered in the very first lecture, which is the CHSH game, right? So, more broadly, we're going to talk about how non-local games can be used for entanglement testing. And really the way we should, you should think about this is that non-local games, of which the CHSH game is like the primary example, is a way to force quantum systems to do what you want them to do. You can classically force them to do specific operations. All right, so let's recall the CHSH game. All right, so I'm going to be drawing lots of these these two prover pictures for the remainder of the class. So we have two players. We call them Alice and Bob, and there's a referee. The referee will choose a random bit, send it to Alice. Choose a random bit Y, send it to Bob. They respond with bits A and B, and they win if the sum of their answer bits is equal to the product of their question bits mod 2. And if Alice and Bob are classical, they use a classical strategy, then the classical value of the CHSH game, and I'll denote that by omega, which will look a lot like W, but omega of CHSH is equal to 3/4. But we saw in lecture that if Alice and Bob share quantum entanglement, then the quantum value, which I'll denote using omega star, the star just means like they're allowed to use quantum entanglement, is a larger quantity. It's this cosine squared pi over 8, was it? Yeah, pi over 8, which is 0.854 ... Right? The strategy, the quantum strategy that they can use to obtain this higher value is pretty simple. This is achieved using, EPR pair shared between Alice and Bob. So it's this simple 2-qubit entangled state, maximally entangled state, and their measurements. We can describe their measurements in terms of these binary observables, right? So if Alice gets question x equals to 0, then she measures this observable, which corresponds to the poly Z observable, right? If she gets x equals to 1, then she measures the x observable, right? Or she measures in the x basis. And for Bob, his strategy is some linear combination of these. And so it's a pretty simple to describe strategy. And using this, they can achieve this quantum value 0.854. All right, and the reason we were talking about the CHSH game to begin with is because we were thinking about this, this Bell test, right? Bell's theorem. Bell's theorem was saying there cannot be a local classical theory that reproduces all of the consequences, predictions of quantum mechanics. And concretely, how this can be used is to say, well, suppose that you ran an experiment, you played the CHSH game with two players, Alice and Bob, and you see that they're winning with higher than 3/4 probability. Then what you're forced to believe is that they're using some kind of quantum entanglement in their strategy. They cannot be using a classical strategy. So if you're running strictly more than 3/4 of the time, means that you're using doing something non-classical. In particular, you're using quantum entanglement. And it's sort of a way to at least verify that nature is behaving non-classically. So that's pretty cool. But we're actually going to go further now because the CHSH game actually tells you a lot more. If you're, suppose that they're winning, not just greater than 3/4 of the time, but very, very close to this quantum value of 0.854. Then, in fact, that they must be using a specific type of quantum strategy. And because of this, we say that the CHSH game has rigidity. Or we say that the CHSH game is rigid. Essentially, there's only a unique way. There's only one way to win the game close to optimally.
Is that one way, given that quantum mechanics is correct, or one logical, theoretically possible way?
Great question. Well, assuming quantum mechanics is correct, assuming that the way that the players are described is using quantum theory, then there's essentially, I'll describe what essentially means, but essentially one way to do it quantum mechanically. So yeah, good point. So within the framework of quantum mechanics.
But I guess this requires a proof, right? Who knows if there's some weird protocol out there that achieves the same winning probability.
Yes, and basically the rest of the lecture is going to be devoted to this proof. So we're going to see why the CHSH game is rigid. And just to prime you, this rigidity will be the thing that allows us to do this verification, because suppose you play the CHSH game, in the beginning, Alice and Bob, they're completely uncharacterized. They may be extraordinarily complicated, using who knows what kind of quantum state, what kind of quantum measurements. But by playing the CHSH game, if you can somehow determine that they're actually just doing this, that's a very powerful kind of characterization. And once you have, this gets your foot in the door, then you can start playing a bunch of different CHSH games together in some, orchestrated, carefully put together way. And then you kind of, this is how you start commanding them to do, you do this operation, you do this operation, and then you control them to do arbitrary quantum computations, just starting from this CHSH game. I'll use a different color. Right, so that's why this is super powerful. All right. So let's prove it. Let's see how we can actually prove rigidity of the CHSH game. So let's just start, all the way at the beginning. There's Alice and Bob in front of you, and you just know that they're described using quantum mechanics. So we have to have a way of modeling arbitrary quantum strategies. Right, so what's a strategy? Well, we can abstractly define it. It's a triple. So, you have to say what state they're using between Alice and Bob, and their choices of measurements, right? So this state is some bipartite state, some entangled state in CD, tensor CD, okay? We don't have any control over what this dimension is. Right, so we just know it's a natural number, and a choice of measurements. So, right, so we know that they're performing measurements depending on their question on this d-dimensional state. So they'll choose d by d matrices, AX0, AX1. These are projectors that sum to the identity. Right? And for both choices of X.
Sorry, Henry, is it important that Alice and Bob have the same number of qubits?
It's not important. I guess you can always sort of assume, like, let's say one person had more qubits than the other. You can always just pad the other person's state with like zeros, and they just ignore it. So it's just a little more convenient to say that they have the same dimensions on their side, but it's not so important.
Okay, great, thanks.
Yeah.
And yeah, go for it.
Does that imply that increasing the dimensionality of one system would never proffer any advantage?
We'll see that, yes. For this specific game. And actually, in general, yeah, in general, it actually won't matter. Like, what really matters is not the local dimension on each side, but really the amount of entanglement between the two sides. That's really the important quantity. Just so like, if this makes sense to you, then great. If not, what matters is just the Schmidt rank of the state that's used between them. And so Alice chooses for both her questions a projective measurement, and so does Bob. So we'll just call it by0, by1, right? So the first subscript indicates the question, and the second subscript indicates the answer. And rather than keeping track of all these different projectors, since they have binary outcomes, we'll just package them into an observable, just because they'll be mathematically nicer. So I'll say that A sub x is the observable A sub x0 minus A sub x1. B sub y is equal to B sub y0 minus B sub y1. And notice that these are observable, so they're actually unitary and Hermitian. So, and another convenient thing about them is that they square to the identity. Like if you square them, it's going to be the identity matrix. Right, so we'll just work with observables because it'll be easier and nicer. So that's what a strategy is. You choose a state, you choose your observables, and that tells you everything about how they'll behave in the game. So if someone chooses a strategy like that, then we can define how well this strategy succeeds in the CHSH game. Right, so this will be defined as, well, you pick questions X and Y with a certain probability, which in this case will be 1/4. You sum over all possible winning answers for that choice of for those questions, and then you look at, well, what's the probability using this strategy? They output AB, right? So I'm just writing out what the definition of what the success probability is, and sort of plugging in the right numbers, we get sum over x, y, a, b, such that a plus b equals x times y. And their success probability is exactly this. Right? Just writing out the definition of, what's the probability they measure A and B given X and Y. But this is still written in terms of projectors, and I don't want to write it in terms of projectors, so I'll write it a slightly different way.
What's phi here? The state there?
Oh, this psi?
Yeah, psi.
It's the state that they chose. So it's this bipartite state right here. It's part of their strategy.
Yes.
So I'm going to look at another quantity, which is not the probability that they win, but rather the difference between the probability of winning minus losing. Okay, and this is just related to the winning probability in this way. And the reason I'm going to use this is because I can write it in terms of the observables. So this is the same as 1/4 divided by times the sum over the questions x comma y. I won't need to sum over the answers anymore because they've all been folded into the observables. So why, these two are equal. This is, you can check this on your own. Right, this is, you just plug in the definition of the observables and you'll see that both sides match. But the point is that we have a slightly simpler expression to deal with. And if you know what the bias is, you can easily compute what the maximum winning probability is, for example, and go back and forth.
So just one more question, which is maybe kind of irrelevant. How do you know that they only make only one measurement? What if they measure the state 1,000 times? Like, yeah.
Mm-hmm. Sure. So great question. So yeah, I mean, they can perform some enormous quantum computation, measure lots of things. The point is all of that can be wrapped into a single measurement, because at the end of the day, they're just giving you one bit.
Mm-hmm.
And the probability of outputting that bit can be modeled as a projective measurement on some state. Yeah. So really this way of modeling strategies, I mean, it encompasses anything they could possibly do within quantum mechanics. Okay, so given this is how we, so someone walks up to you with some strategy, the first thing that we're going to prove is something called Searlson's bound. And this is really going to show that this 85% value is really the optimal value. That the quantum value of the CHSH game is at most cosine squared pi over 8. Like there's no quantum mechanical strategy that can allow you to win with probability, say 1. Right, so this number, this cosine squared, is actually equal to 1/2 plus 1 over 2 root 2. And this is equivalent to saying, and I'm going to write in terms of the observables, is that this operator that's sandwiched by psi is at most 2 root 2. Okay, so this is the thing that, you know, this expression, maybe you've seen it before if you've like taken a quantum class before. This is called Searlson's bound. It's, you know, named after this mathematical physicist, Boris Searlson, who actually, you know, just passed away pretty recently, like this January. But, you know, he's famous for proving a lot of things about these non-local games, like way before anyone else was thinking about them. Okay, so let's just keep on transforming this expression into something that we can, you know, actually prove. So
are the minus and plus signs correct there?
Yeah, there should be one minus sign in when they both get question 1, and then plus everywhere else.
Okay, I'm not seeing that, but I'll look at it carefully afterwards.
So let's see. So here, one way to see this is that you only pick up a minus sign when x times y is equal to 1.
Fair enough. I forgot about that minus sign there.
So yeah, these two should be the same. And okay, so his bound is saying that this equation is, or this inequality is always true no matter what observables ax, b, y you choose, and no matter what state you choose. So this is equivalent, since, you know, you're also maximizing over the state. This is saying that the that the operator norm of this, you know, of whatever matrix this is at most 2 root 2. Right, okay, I've written these C1, 0 and C1. What are these? Well, I've just collected the B's. Right, you can verify that if you plug in C0 and C1 as I've written them, then this is really just the original expression. Right, so this is because the operator norm of a matrix, this is just defined to be the, you know, you take the supremum over all possible states you know, M sandwiched by this matrix. Like as long as M is a Hermitian matrix. But this is one definition of the operator norm. Okay, so this is really what we want to prove. Just this statement.
Henry, I think the bound on the right-hand side should be 2 rather than 2 root 2.
Oh, yeah. You're right. Because I've already divided by the root 2. Oh, good catch. Thanks. Yep. Yep. So yeah, if you plug in C, hopefully, yeah, everything should match. Okay. And I'm going to take another step, right? And maybe this is like coming out of nowhere, but this is really how he came up with it. How do you prove this? Well, I'm going to prove another statement, which is that if I square this quantity, that the operator norm of the squared matrix is at most 4. Okay. Why is that? Well, because if this comes from if you take the operator norm of a squared matrix, this is the same as the square of the operator norm. So if I prove that this, that this is less than 4, then this must be less than 2, right?
Wait, why do we have 2 there? And before we had 2 square root of 2, where did this? Oh, okay. You divided by it in the C's. Yes.
Yeah. Yep. So the square root 2 moved into the C's. Yeah. The reason why we're squaring this is because actually, when we expand it out, we're going to get some nice cancellations. Right? So let's start opening things up. We're going to get A0 squared tensor C0 squared. We're A1 squared tensor C1 squared. And then we're going to get a bunch of cross terms. So we'll have A0 A1 tensor C0 C1 plus A1 A0 tensor C1 C0. And just maybe obvious, but these things are not the same because A0 and A1, C0, C1 don't necessarily commute, right? So we got to keep track of both of them. So that's, if we open it up, that's what we get. And now we're going to start taking advantage of the fact that we know the A's and B's are observables that square to identity. So let's evaluate each term separately. So A0 squared tensor C0 squared, this is identity tensor. And we just have to square the C0 thing, right? So this is going to be, you're going to pick up a 1/2 on the outside, right? That's, you square the 1 over square root 2. We're going to B0 squared plus B1 squared, and then you're going to get the cross terms, right? We know that this is also 2 times identity. So I claim that we get identity plus 1/2 B0 B1 plus B1 B0. All right, next square term.
Shouldn't B0, B1 equals 0?
B0, B1, this one here?
Yeah, and the same for the other one. Because if it was a Z basis, it would be, you would have a 0, 1, like a product between 0 and 1, right?
Oh, so these are the observables corresponding to the 2 different questions. So B0, B1 are observables. So we don't know what the relationship between the 2 are. And so let me go back to our definition. We just know this.
Right. Okay, yeah, and if it were by0, by1, this would be 0.
Yeah.
Okay, yeah, I'm confusing it. Okay,
Yeah.
sorry.
Actually, yeah, actually it might help, like, as a mental model, just in like the canonical textbook strategy, actually, yeah, you might find this helpful. So A0 should be Z, A1 should be X, like the Pauli operators, and then B0 is equal to this, like, 1 over square root 2, Z plus X, and then the B1 is equal to Z minus X. So if you want to like sort of do a sanity check on what this should be, then you can plug in these operators and see what you get. But in this arbitrary strategy, we don't know what it is. They're just like, arbitrary d-dimensional observables, but we do know that they square to the identity. Okay, so just working out the algebra, you get nearly the same thing, except you pick up a minus sign, right? So if you sum these up, you get 2 times the identity, I believe. Right? Okay, so I'm going to give, I'm going to call this equation star, so I'll refer to it. So star is now equal to, we have 2 times the identity, right? Tensor identity, plus, we still have these cross terms. Oops. And now I'm going to use the triangle inequality for the operator norm. So we'll have 2 times the identity plus A0, A1. Right? And we know that the operator norm of twice the identity is at most 2, right? Well, it's equal to 2. And also we know that the operator norm of a tensor product is just the product of the operator norms. Okay. And I've used just a couple facts, like, for example, like if you have the product, it doesn't matter which order you compute them in, for example. Okay. So we're almost done. We just need to start bounding these operator norms. So one thing we know is that A0 times A1, what's the operator norm of this?
I would say at most 1 because it needs to work.
All right, that's the good student answer. So we know A0, A1 are unitaries, right? And unitaries have eigenvalue that's on the unit circle. So the operator norm has to be exactly 1. Right? And good. So now we just need to compute C0 times C1, right? And here we just have to expand out what this is. This is B0 squared plus minus B1 squared plus these cross terms. Oh, oops. All right, so we know that these are both identities, so they cancel out to be 0. So this is equal to 1/2 B1, B0 minus B0, B1, or maybe the other way around, but it doesn't really matter. And here we don't, again, we're going to use the triangle inequality. So we pick up a factor 2, but this is all equal to 1. So just plugging everything in, we get 1 here, we get 1 here, and we finally get the desired bound, which is all of this is less than 4, and it all works out as we hoped. So we've deduced that, we've deduced the Searleson bound, okay? And this shows in kind of just by plugging through this algebra that 85% is 0.4% is the best you can do in the CHSH game. Okay, so maybe let's take like a 5-minute break. So let's come back at 5:11, then we'll continue on.
Henry,
Mm-hmm.
you maybe explain that triangle inequality step one more time? Like, does a minus sign make it weird at all, or?
Let's see. You mean this one here?
Yeah.
I guess you can just treat it as like, you know, this is like B1, B0 plus minus B0, B1.
Yeah.
And just treat the minus B0, B1 as like just another operator. Oh, I guess the other thing is that the operator norm of minus an operator is just the same as the operator norm of the operator itself. So like norm of minus m is equal just to the norm of m.
Yeah.
So does that make sense? Right. And also, you know, a plus b is at most norm of a plus norm of b. So if you put those two things together, then you get the triangle inequality statement.
Thanks.
Yeah. Okay. Yeah. Any other questions about like this derivation? Okay, so let's move on. So we've seen like there is a non-trivial upper bound on how well you can do. And we're actually gonna kind of build off of this proof to prove this rigidity statement. So just to keep things simple, I'm going to like analyze, show like rigidity for the case of when you have a strategy that exactly achieves the optimal value. So let's say that someone walks up to you with an arbitrary strategy for the CHSH game where the value is equal to, you know, cosine pi over 8. Then we want to do something about the, you know, the structure of the strategy. Like I'm claiming that it's essentially the same as this canonical qubit strategy, but then you say, well, how can that be possible? Because this strategy S could be d-dimensional, right? Like for d equals to a gazillion, right? Which is much greater than d equals to 2. So I have to explain what exactly I mean by them being the same. So this is the exact CHSH rigidity. And the statement's a little technical, but we'll like kind of unpack it and see why it makes sense. So you know, suppose that you have this strategy like this, then there exist. Okay, so actually before that, let me just draw a picture. So you have a state psi, and let's imagine that it's on two rigid, you know, each of them is d-dimensional. Each side is d dimensions, right, for Alice and Bob. And I'm going to give Alice's space a name. I'm going to call it script A, and I'm going to call Bob's space script B. So these are their register names. Right. I'm going to try my best to like write the scripts in the correct curly font. And so we view like the observables A0, A1 as acting on Hilbert space script A, and then B0, B1 as acting on space script B. and I'm going to use these register names to just keep track of when different operators are acting on which sides. Okay, so back to the theorem. It says that there are going to exist local basis changes. So technically speaking, there's going to be an isometry. I'll explain what an isometry is later. It's, you can think of an isometry as a unitary for now. So it's going to be some change of basis that maps, say, Alice's space into a new space that I'm going to call script A1 and script A2. There's going to be another isometry, but this time for Bob. And it's going to map into B1 and B2. Okay, what are these A1, A2, B2, B1, B2? Well, the A1 and B1 are going to be isomorphic to C2. So this is where the qubit is going to appear. And then the A2, B2 is going to be isomorphic to some other space, CD, D prime, for some D prime that I don't really care about. It's just some integer. So it's like a local basis change where you kind of like reorganize the basis states where you've kind of identified. So, when you apply V tensor W to these two spaces, you're going to see a slightly more complicated space where there's A1 and B1 here, and this is going to be a two-dimensional space. It's like enough to hold one qubit. And there's going to be A2 and B2. And this is going to be a larger space, but we call it the junk space because we don't really care what's happening here. Right, and put together, all of this is going to, like, this space is going to be, C2 tensor CD prime, tensor C2 tensor CD prime. Right, so that's what these linear maps are going to do. Okay, so what do we do with those linear maps? Well, it's basically kind of like, you can think of it as changing the basis so that when you apply it to the strategy, you actually see that the strategy was just really hiding the original canonical qubit strategy. So if you define a new state, which is like, I'm going to take this V tensor W and apply it to the state that's used by Alice and Bob in this strategy, then this state, well, hold on, such that if you let, theta equals this rotated state, then you see that it's actually factors as an EPR pair between registers A1 and B1, tensor some junk state. I write junk because we don't actually care about characterizing. It's just some other state that lives in registers A2, B2. Right, so from this arbitrary state psi, we've picked out the existence of an EPR pair.
How can you guarantee that it's pure in that way?
Well, this theta is going to be pure because psi is pure. We're assuming psi is pure. And you're applying an isometry or unitary, so that will keep the purity. So, so therefore it has to be pure, and in fact, it's going to factor in this way. So that's maybe the surprising thing.
I mean, to pick up on that, like maybe how do we know there aren't really complicated correlations here that prevent you from doing that?
Oh, you mean how do you know there might not be entanglement between these registers and this register?
Sure, yeah.
Oh, well, it's because you're starting with the constraint that they're winning the CHSH game perfectly. So this constraint is so strong, that there cannot be any like there must be somewhere in this crazy d-dimensional space that they're starting out with, you can identify an EPR pair and extract it out. And all the action is going on this EPR pair.
So are you assuming that, or you're proving it?
We're proving it. So, okay.
Well, like,
So this is the
my
conclusion. Sorry, go ahead.
like, am I correct in stating that once we prove that we have an EPR state there, then by the monogamy of entanglement, we can now state that these two qubits cannot be entangled with anything in the junk state.
Yeah, although you don't even need to go that far. Like the fact that I've written as an EPR pair that are like sort of just by definition, it cannot be entangled with anything else.
Okay.
So there's one more part to this theorem, which is to say, well, what about the operators? So that this will look like this. So it says, you know, suppose it's kind of like, well, I'll just write it. Okay, so this is kind of a mouthful, but let's parse what it means. Okay, so let's just start with this. It's saying, you know, consider two different ways of doing something. Imagine that you took the state psi that Alice and Bob started with, and Alice just applies as a unitary this operator A0. So remember A0, it's an observable, it's a unitary, so you can just apply it to the state. A0 only acts on Alice's part of psi, right? So you do that, and then you apply this basis change. This is the same thing as if you started with the basis change state, like you change the state first, and then on the EPR pair, you apply the Z operator on the qubit. So it says that really, as complicated as A0 might look, after you've done the basis change, all it's really done is just performed a 1 qubit operation on the EPR pair, and it didn't do anything to the junk state. And okay, so the rest of this should make more sense. So then you say, well, what if I did A1 instead of A0? Under the same basis change, it looks like an X operator on the EPR pair on Alice's side. And then same thing for Bob's operators. Like there is a basis change that looks like a Z on B1 on this part, or X on B1.
Why is it just Z and X and not Z plus X and Z minus X?
Oh, good question. So you're right. So you're saying, well, this doesn't exactly look like the canonical strategy, but it turns out that, so I'll write it in blue. There's like another, because there's a local basis change where there's a 2x2 unitary U where you can really map X and Z to Z plus X and Z minus X. So I'm just kind of folding it. I'm already folding it into these local isometries. So actually, in this way, it actually makes the description of the CHSH strategy a little more simpler, because you just say, oh, well, Alice and Bob are just using Z and X, but Bob will have to first perform a basis change to do that. So did someone else have a question? Okay, so that's the statement. I mean, it's kind of long, but hopefully it should, intuitively, it just means that we've really identified in this arbitrary strategy that succeeds optimally in CHSH, this qubit, this EPR state, and these single qubit unitaries that act on the EPR state. And there might be this other junk state, but nothing interesting is happening there.
So can we say something about the uniqueness of these V and W?
The uniqueness of the V and W.
Yeah.
Oh, I guess it's...
Or the final four conditions, do they imply something about the uniqueness?
Let's see. They're not unique for some trivial reasons. Like, for example, so they're isometries. Oh, okay. At first I should say what isometry is. So isometry, it's just a length preserving map. So let's say you have an isometry from space A to space B. It just means that the dimension of B has to be at least the dimension of A. And then for all X in A, the norm of V applied to, the norm of X has to be the same as the norm of V applied to X, right? One way of thinking about what an isometry does, it sort of, it applies, you can take the state, the input state, you tack on some ancilla zeros, and then you apply a unitary on that bigger, like, concatenated state. That's what an isometry is. So one thing that these isometries could always do is just tack on additional zeros onto the junk state. And so it wouldn't be unique for that trivial reason.
Right, right, okay.
So yeah, so I guess it's it's sort of a lengthy theorem, but it's worth sort of like mulling over, sort of trying to see like, I mean, it's really constraining it. Like it says that you can really extract out this simple strategy, no matter what crazy strategy you might have walked up with. And so how do you prove such a thing? Like, how do you locate this EPR pair to begin with? And so the proof of this theorem goes in 3 steps. So, again, someone hands you this arbitrary psi AB in D dimensions. The first thing we want to establish, and the most important thing, is that you want to establish some anti-commutation relation. Meaning that if you looked at Alice's observables, A0 and A1, you can multiply them together and apply them to the state. And it will turn out that if this strategy actually wins the CHSH game perfectly, then in fact, it forces these observables to have this anti-commutation relation, like A0 times A1 is equal to minus A1 A0, as long as you're operating on the state. And similarly for as a sanity check, this should make sense for our actual operator, like for the canonical strategy, because if A0 is Z, A1 is X, then we know that they do, in fact, anti-commute. So this is like a legitimate thing to prove. And another thing is, it's kind of weird that you would be able to deduce this, right? Like, in the actual game, when you're playing this game with Alice and Bob, they're only ever applying one measurement at a time. They're either doing A0 or A1. They're never doing A0 and A1 at the same time. Yet somehow we're able to deduce some relationship between those two operators. And really that's at the crux of it. So let's say you establish that. Then from this is already enough to help you identify a qubit within their strategy. So right, so we'll get these isometries V and W. And then the very last step is just to identify the EPR pair. Okay, so let's carry out these steps. Let's show that anti-commutation must hold. Okay. So let's start with the fact that this strategy is optimal. So then it actually means that this previous expression saturates Searlson's bound. So not only is it at most 2, it's actually exactly equal to 2. Okay, and we're going to just get a lot of mileage out of the fact that this is exactly equals. So let's see, what do I want to argue here? The first thing I want is I want to argue, okay, so C0, remember that C0 and C1 are like these linear combinations of the B0, B1s. C0, you don't know immediately that C0 and C1 are observables or even unitaries, right? So we actually first want to establish that they are in fact unitary. So we want to know that C1 times the state, C0 and C1 times the state are unit vectors. Right, which we don't immediately know off the bat. So let's see. Okay, so to prove this, we're going to use the Koshi-Schwartz inequality. Right, so what's Koshi-Schwartz? Like if you have two vectors, just a reminder, like the inner product between two vectors of V and W, if you square them, it's at most the inner product of V with itself times the inner product of W with itself. Right? So let's say that V is equal to the observable A0 times psi. And let's say W is C0 times psi, right? And if we apply the Cauchy-Schwarz inequality, then this A0 tensor C0 is at most, so this is Cauchy-Schwarz. It's V inner product itself, so that'll be A0 squared tensor identity times C0 squared. I'm going to leave off the identity. This is equal to 1, right? Because A0 squared is the identity. And now we just have to figure out what C0 squared is. But we actually calculated it before, so I'll just write it out. Like, if you work out the algebra just by plugging it in, it's these cross terms. Right? And if we do the same thing for the A1 and C1 term, this is at most. Everything's the same except we have a minus sign. Okay, and now let's use the fact that they saturate the serial sim bound, right? So if I call those quantities 1 and 2, I have that 1 plus 2 is equal to 2, right? This is from optimality, right? But they're also at most this 1 plus alpha plus 1 minus alpha. Alpha is just this 1/2 B0, B1, B1, B0, right? But the only way that, I mean, you can just like, you know, deduce this or run it through Mathematica or whatever. This is only possible if alpha is equal to 0. Okay, and it's not hard to see, but you know, you can take my word for it. So if alpha is equal to 0, I mean, already that should be really suggestive, right? Like it should tell you that this thing is, I mean, this looks like the anti-commutator of B0, B1, right? So we're almost there. But what it tells you is that not size 0. What it tells you is that C0 squared and C1 squared is equal to 1. Or, in other words, that these vectors have unit norm. Right, and like that was the first thing that I wanted to show. So C0 and C1, like they look like unitaries. Okay. Okay, so we're basically there. We just need like a couple more things. So we know that they have unit norm. So now let's look again at this this equation, right? The fact that we have saturation of the serial sim bound. This is, you know, these two sum to, they're equal to 2, but this is the inner product between two unit vectors, right? Like A0 psi has norm 1, C0 psi has norm 1, as we just proved. So when you take the inner product of two unit vectors, their norm can be at most 1, right? And you know, the same thing here. So this tells us that A0 tensor C0 psi, like they both have to be 1, like they can't be anything else. Right? They couldn't be any other number. But what does that tell us? I mean, you can view this as the inner product of these two vectors. And you know, if you take two vectors, unit vectors, and you take their inner product and they have inner product 1, that must mean they're the same vector. Like they have to be exactly the same. So we get this really cool fact that A0 times psi is equal to C0 times psi. And similarly, and the reason this is cool is this is called operator switching, right? Meaning that here's an entangled state. if you apply Alice's observable A0 as a unitary, that results in the exact same thing as if Bob applied C0 on his side of the state. Or, or whenever you see an A1, you can switch it with C1 or vice versa. And that's really useful, like, because, and this is the final step for this anti-commutation, I wanted to show that A0 and A1 anti-commute, right? So what happens if I look at this expression? Well, I can split it like this just by linearity. And so this thing is A1 times psi. I'm going to apply operator switching. So A1 times psi is the same as C1 times psi. Right, just from above. And this is A1 tensor C0 times psi. But then we can just apply it one more time, right? This is the same as, right, we can imagine that this is identity tensor C1 times A0 psi plus right, we can just apply it one more time because now we have an A right next to the psi. This is equal to C1 C0 times psi plus C0 C1 psi. And the point is that if you expand out what C1 and C0 are, right, they're written in terms of these B's, this is exactly equal to 0. And this is exactly what we wanted because, right, this is equivalent to A0 A1 times psi equals to minus A1 A0 psi, right, which is the anti-commutation that we wanted.
Can you please explain the transition where you use the other switching? Like, why can you apply it there? Like, you don't have it as written in your equations there, or am I not seeing something? Like,
oh, I guess, yeah. One thing is that sometimes I've left off the identities. So whenever we see an A, or technically it's supposed to be a tensor identity.
oh,
and whenever
okay.
we see a B, it should be identity tensor B or identity tensor C.
And
So
then in the next line, you then have an identity before the C.
yeah. Right.
Okay.
It's just to sort of save space.
Mm-hmm.
Yeah, good question. So yeah, that might look a little mysterious. Right, so it's like a lot of algebra, but like really all the maneuvers that we're using, we're just using the saturation of the Searlson bound a couple times, and we use the fact that A0 is an observable, so squares the identity, and really the only non-trivial thing that was going on was this Koshi Schwartz. although I personally think most of what's non-trivial in mathematics can all be boiled down to some clever use of Cauchy-Schwartz. But, so we got the anti-commutation statement we wanted, and then of course you could have carried all of this out for Bob's operators, right? So by symmetry, B0 B1 psi equals minus B1 B0 psi. All right, any other questions about the maneuvers we did or this proof? Okay, so that was basically most of the detailed algebra that we'll talk about. Now I'll just kind of like give an overview of these other two steps. So we got these anti-commutation steps relation. Now I claim that from this we can extract this qubit structure. I'm not going to prove this. Like I think I might put this on the next problem set or something. But I'll just write what the statement is. So so here's I'll write down a proposition. So let's say you have and I'll just write it like generically, like so, so that's abstracted away from what we have before. So let's say you have a bipartite state, and you have two binary observables, A0, A1, acting on the A space, such that A0, A1 apply to psi is equal to minus A1, A0 applied to psi. Then there exists this isometry local in the sense that it only acts on A, where this A1 is isomorphic to C2, such that, I mean, it'll just be like 1/2 of the original theorem statement that we had. So if you had V applied to A0, this is equal to Z acting on A1, applied to V psi, right, so this is just like a generic fact about anti-commuting operators. Basically, whenever you see anti-commuting operators, morally speaking, you've located a qubit. Like you can perform some basis change on which those two anti-commuting operators look like the Z and X operators acting on a two-dimensional space. So this is just some like linear algebraic fact. So actually, in a lot of these, like these verification protocols and these verification papers, this is like a very common theme that comes up is like, well, you're interacting with something that's completely uncharacterized. How do you know like how many qubits they have, or whether they even have a qubit? And in some sense, it's like kind of not. It's hard to say, like, without peering inside the box, like, how do you know that a qubit exists? But the point is that if you can identify anti-commuting operators, then that defines what a qubit is. Right? Like, you don't know what basis or reference frame that, this device or these two players are using. I mean, they're using an arbitrary reference frame, but you don't really care. The point is that, that if you have two anti-commuting operators, then there's a reference frame under which those two operators look like they're just acting on a single qubit. So you just say two anti-commuting operators, that defines a qubit. So that's like a very, think of, it's a simple observation, but I think a very powerful one. And so, this proposition is, may show up on the next problem set. And it's really the basis for a lot of these verification protocols. Okay, so that gives you the qubit structure, and now you have to find the EPR pair. Right, so clearly, you apply this proposition once for Alice and once for Bob, and you get these two isometries, one V, one W. So let's see. Okay, so how do we find this EPR pair? Well, let's go back to some of the relations we discovered. We found out that A tensor 0, A0 tensor C0 is equal to 1. A1 tensor C1 is equal to 1. I mean, this is just the same as this. Right? I mean, we basically proved this in the anti-commutation step. So let's apply our isometries V and W that we found to both sides. So we apply isometries VW, A0 tensor C0 to psi, right? And the role of these isometries is really to just make A0 and C0 look like X, or sorry, the Z operators, right? So this is Z and Z applied to A1 and B1 on the basis change state, right? But on the other hand, we know that this is the same as VW applied to psi. Right? So all three things are equal. What's another thing that we know? Using the same exact reasoning, we get that V tensor W applied to psi is equal to X tensor X on V tensor W psi. Right, so let's call this theta, right? So theta is a state on 4 registers, right? It's A1, B1, A2, B2. And so just to draw it like this, I'm going to reorganize the registers a bit. It says that if we applied Z and Z on these two qubits, it leaves the state unchanged. And if we apply X tensor X on these two qubits, it also leaves the state unchanged. And that is the same as saying, like, if you measured these two qubits in the Z basis, you get the same outcome. And if you measured in the X basis, you get the same outcome. So this should start ringing a bell. Like, where have you seen this before? So what does this imply?
EPR.
Exactly. It implies that in the A1 and B1 registers, it has to be an EPR pair. It can't be anything else. Right. And that's it. I mean, we've basically proved the rigidity statement. We have this local basis change. It gets us the Z and X operators, and we found extracted the EPR state. Any questions about the proof?
This was heavy.
Yeah, there's a lot of steps. I mean, don't worry if some of the details went past you. Just remember just the main three steps. Winning optimally means you know that they have anti-commuting measurements, and from then it's sort of like that's the most important thing. Then you can identify the basis change and identify where the qubits are and so on. So that's the thing to remember.
Also, when was this proven? Like how long after the proof of the Bell's theorem, I guess?
Oh, quite a while. So I think the earliest, people reproved it a bunch of times, but I think the earliest time that it was noticed was in the late 80s. So this is, I think the first proof, I think my history is a little murky, but I think it's due to Summers and Werner in 87. And I think Cyrilson might have also realized it, but he maybe didn't bother writing it up. Maybe sometime in the 80s. And then I think it was like rediscovered in the computer science world. Hold on, who was it? I don't know, sometimes like 2004. I forget who, I know that Andy Yao was on the paper. So it was proved in a bunch of times separately by different people. Okay, so the last thing I wanted to mention was, this proof, yeah, it's heavy, has a lot of steps, but there's one big thing that you should be dissatisfied about, other than the fact that it's long. Wait, where did the rigidity statement go? Yeah, so you might be dissatisfied with the fact that we only proved exact rigidity, but how do how often can someone give you a strategy that wins with exactly a certain probability, right? Like, how do you even test that a strategy has, cos squared pi over 8 success probability? I mean, you can, right? You're just playing this game multiple times and you're just trying to estimate how often they win. And you can only know that they win with, say, 84% or something, right? So suppose that you know that they're winning with probability optimal minus epsilon. What can you say about their strategy? And it turns out that you can basically say the exact same things, except instead of equality, you just have approximations. So what's true is approximate rigidity. So you say, suppose that the value of your strategy is at most you know, the cos squared pi over 8 minus epsilon for some epsilon, then it implies that this theta, like there's still these local isometries, it's going to be not exactly, but square root of epsilon close to this EPR. And all of your operators approximately look like the you know, the Z and X operators. Right, so it's really the same thing, but you just put square root epsilons everywhere. And this is really the thing that's most useful in practice, because of course you can never know that they win perfectly, but that they win close enough to perfect. And it's the same proof, you're just keeping track of all the epsilons.
And is this known to be a tight trade-off, or?
Yeah, the squared epsilon is necessary. So yeah, you know, it sort of gives a smooth trade-off between how close you are to the optimal strategy and how close you are to winning. Okay, so you know, we're at the hour. So that's it. Next time we're going to use this as a black box to start commanding our quantum computers to do the right thing in a verifiable way. And oh yeah, and you know, reminder, the project proposals are due this Friday. So thanks a lot.
By project proposals, you only mean that we need to send you a mail, right?
Yeah, just a one paragraph email.